Most students are taught to solve waves using equations that look like Schrödinger's equation. They use complex numbers, eigenvalues, and modes, and it works. But physics quietly moved beyond that approach long ago. Here is what really happened. In 1865, James Clerk Maxwell unified electricity and magnetism into a set of 4 equations that predicted electromagnetic waves. But solving Maxwell's equations directly for real systems was extremely difficult. In the 1880s and 1890s, Heinrich Hertz and Oliver Heaviside introduced practical tools and frequency domain thinking that converted these equations into wave equations with complex numbers. This allowed engineers to track phase and interference using elegant mathematics. In 1926, Erwin Schrödinger introduced his famous equation for quantum mechanics. Because both light and matter behave as waves, physicists noticed that many electromagnetic problems could be rewritten in a Schrödinger-like eigenvalue form. This created a powerful but limited tradition of mode-based frequency domain analysis. For simple cavities and atoms, this worked beautifully. But as physics advanced into real materials and real devices, its limitations became obvious. In the 1940s and 1950s, Julian Schwinger and Richard Feynman developed quantum electrodynamics, replacing single-wave equations with full quantum field theory. Here, fields, particles, interactions, and radiation were handled together, and Schrödinger's equation became only one representation among many. In the 1960s and 1970s, Carl Yee introduced the finite difference time domain method, allowing Maxwell's equations to be solved directly in time. This revolutionized optics, antennas, microwave engineering, and photonics by capturing pulses, dispersion, nonlinear effects, and broadband behavior in one simulation. In parallel, scientists like Harrington and Poggio developed integral equation and Green's function methods that transformed scattering, radar, and nanophotonics by focusing on sources and radiation rather than artificial modes. By the 1980s and 1990s, modern finite element and boundary element methods emerged, giving engineers the freedom to design complex waveguides, photonic crystals, and microchips that could never be handled by Schrödinger-style equations alone. Today, physics and engineering rely on hybrid computational frameworks, combining time domain solvers, field theory numerical optimization, and statistical methods, each chosen for the structure of the problem. The Schrödinger-like formulation remains a beautiful doorway for learning. But the real engine of modern science is a city of methods built far beyond that door. Schrödinger gave us a key. Modern physics built the world.